Bismillahirrahmanirrahim. Assalamu alaikum dear students. I hope you all are fine and in the best conditions of your health. So for the course of organic reaction mechanism, today we shall discuss about the stereoselectivity. The key concept which we shall discuss is the stereoselectivity, specificity, then we shall study about the stereoselectivity and also some advanced terms like prochirality, homochirality, re and psi phases, enantioselectivity and diastereoselectivity. Right, so as we studied about in the previous lecture, that whenever we carry out a reaction and we get two products, one of them is major and another of them is minor, it means this reaction mechanism is favoring one product over the other. Furthermore, if you have two reactants which are reacting to form the same product, then in case if one of the reactant is reacting faster, it means that mechanism is promoting that reactant over the other reactant. So whenever there is differential reactivity or there is different amount of formation of product, then the concept of selectivity comes into existence. So selectivity is basically of three types. The chemoselectivity, which is concerned with selective reaction of a particular functional group. Then we have regioselectivity, which means that a reaction site particularly reacts faster, or a reaction is more favored on a specific site rather than the other site. While the third category is stereoselectivity. The stereoselectivity is concerned with which of the two stereoisomers react faster, or which of the two stereoisomers is formed in more amount, right? So the stereoselectivity has also two aspects. It has the aspect of either the reaction of the two stereoisomers, right? So when you are considering the reactivity of two stereoisomers, then we'll consider the rate of reactions. So we shall see that which of the two stereoisomers is reacting faster, and when you are considering the product, then we shall see that which of the two stereoisomers is forming in more amount. So this is called stereoselectivity. So just in order to elaborate this concept more, so let's consider a situation in which more than one reaction can occur between two reactants under the same condition, right? For example, so this is the reactant A and this is another reactant B, right? So when these reactants react, then they can form more than one product. So they can form C and they can form D. So the mechanism of formation of C is different from mechanism of formation of D, right? Because they might involve different reaction intermediates during the process. Just consider that this A and B, right, they react to form two different stereoisomers, right? And one of the isomer is major and other isomer is minor, right? So here is an example in which the reaction is favoring the formation of this product, this stereoisomer, right? So since there is selective formation of this stereoisomer, so this is an example of stereoselective reaction, right? Let's consider another reaction. Here we have two reactants A and B. They are forming C and D, but both C and D are formed in equal amount. So whenever the two products are forming in equal amount, then such reaction is not showing any preference for any of the products. Such reactions are said to be non-selective. So this is a non-selective, non-stereoselective reaction. Right, so stereoselectivity can be described as a process in which different reactants react at different rates to form same product. So let's consider that we have two reactants A and B, and they form product C and D. Similarly, we have two other reactants E and G, and they are also converting into C and D. So the product is same, but the reactants are different. But you can see here that these two reactants are reacting faster to form C and D, right? So this is stereoselective reaction in which the stereoselectivity is being determined by the reactants, right? So since the rate of reaction of the two possible reactions are different, although the product is same, so because rate of reaction is faster for this reaction, it means this reaction is more favored. So whenever there is the concept of favor, so it means that is selective reaction. So this is stereoselective reaction. So now consider another reaction. So again we have A and B, they are converting into C and D, And further we have E and J, they are also converted into C and T, but you can see the rate of reactions are equal, right? So since the rate of reactions are equal, it means there is no preference for any of the reaction to react at a faster rate. So this is an example of non-stereoselective reaction, right? So you should keep certain things in mind, right? Number one thing is that the stereoselectivity is even present when the reactant is achiral. Achiral mean that does not have a chiral center, right? So in such situation, when your reactant is achiral, then product will be chiral, or product will be a stereoisomer, right? So it's not necessary that for a reaction to be stereoselective it must possess a chiral center, right? You can have a reactant which is achiral. So you can have a reactant which has a double bond, you can have a reactant which is not chiral at all, but under such situations the product will be a stereoisomer, right? So the stereoselectivity may be enantioselective or may be diastereoselective, right? But before understanding the stereoselectivity and stereospecificity, is important to understand some key concepts that will be used in the stereochemistry or stereoselectivity reactions. So firstly is prochiral, then homochiral, enantiotopic, diastereotopic, rephase, and psi-phase. Firstly, prochiral. So consider that you have tetrahedral carbon, right? Tetrahedral carbon is a carbon that has four groups attached to it. So if tetrahedral carbon can be converted into a chiral center by changing only one of the attached group, right, then such a carbon is called prochiral center. For example, just consider that we have this carbon. It is tetrahedral center because it has four groups attached to it. You can see that two of the groups are different, but the two of the groups are same. But if we can convert one of these group into some other group, for example 4, then this carbon will have all different 4 groups attached to it. And you know that if a carbon has 4 different groups attached to it, then such a carbon is called chiral center, right? So this is not a chiral center, but it can form a chiral center. So such a center in which if we replace one of the two groups which are same by some other group such that the 4 groups become different, then such carbon or such center is called prochiral center, right? For example, just consider this carbon. So here you can see this carbon is attached to a carbon which is attached to an amide group, and this carbon is attached to a carbon which has a hydrogen group attached to it, right? So you can see that these two carbons are different, but these two hydrogens are same. But suppose that if we replace one of the hydrogens with some other group, right, then if we replace suppose this hydrogen with a chlorine, then the 4 groups which are attached to this carbon will become different, right? So it will become a chiral center, but at present this carbon is not a chiral center, but it can form a chiral center. So this carbon is called a prochiral center, and the hydrogens which are attached to a prochiral center are called prochiral hydrogens, right? So whenever you have a prochiral hydrogen attached to prochiral carbon, we can designate them just like we designate a chiral center, right? So you know that whenever a chiral center, you can assign the configuration of chiral center by means of RS system. So in case you have a prochiral hydrogen, right, say this is carbon, this is a prochiral center, you can say it's an ethanol molecule. So we have an alcoholic group, then we have CH2 group and a methyl group here, right? So these two hydrogens, they are same while these two groups are different, but if we replace either HA or HB by some group which is different, then in that case we'll get a chiral center, right? So these protons HA and HB, they are the prochiral hydrogens, right? So if we want to designate or assign some RS configuration to such system, then we make use of a modified RS system, right? So suppose that we either replace HA or HB with another substance. Suppose that we replace HA with deuterium, right? So if HA becomes deuterium, then this carbon will become chiral because the deuterium is is a different different atom than this HB, right? So since we are attaching 4 different groups to this carbon, so this carbon will become chiral center, right? Let's consider that we are naming the prochiral center, right? So let's assume that we replace HB, right? So this is HB, right? So we are replacing this HB with deuterium, right? Just imagine that there is a deuterium here, right? Then molecule will become chiral, and the stereocenter will have an S configuration, right? By S because deuterium has higher priority. So just imagine that we have replaced this HB with the deuterium, right? So if we have a deuterium here, then you can see you can assign the configuration here. So first configuration will be assigned, first preference will be assigned to hydroxyl, second to methyl, then we have this deuterium, third preference. So in that case you can see that we can carry out the configuration. So if we rotate, if we go from higher preference to lowest preference, you can see this is anti-clockwise, right? So since that's anti-clockwise, then the configuration will be S, right? So it means that this HB has HS configuration, and we say that HB is pro-S. Why pro-S? Because if we replace this HB with some other group, then in that case the configuration of this carbon will be S, right? Let's consider that if we replace the HA with a group which is deuterium, right? In that case you can see that this group will become deuterium. Again we have to carry out the assignment. So 1, 2 and 3. So since this group is below the plane, is away from the plane, so what appears will be opposite. So the configuration, although it appears to be anti-clockwise, but since this group is below, it's away from the chiral center, then we have to invert the configuration, right? So the configuration of this HA will be R, right? So this HA will be considered as pro-R. Why pro-R? Because if we replace this HA with some other substituent, then the configuration of this carbon will be R, right? So in this way we can carry out the RS configuration. We can make assignment, or we can make designation for the prochiral hydrogens here, right? So know that, sorry, let's go beyond, right? So if we change HA to deuterium and leave HB as such, then the configuration of the molecule will become R. So HA is called the pro-R hydrogen and is labeled as HR, just like that one. So you can see here that the molecule is designated as HS. So this hydrogen is a pro-S and this hydrogen is a pro-R. Now next term is enantiotopic and diastereotopic. So you know that we have designated these hydrogens as pro-S or pro-R because this carbon has a prochiral center and these hydrogens are prochiral, right? But here we have another term, it's known as enantiotopic. If we replace either HS or HR with some other atom like deuterium, and if we get enantiomer, then these protons are called enantiotopic protons, right? By replacing any of the 2 prochiral hydrogens, if we get an enantiomer, then these 2 hydrogens will be called enantiotopic hydrogens, right? For example, you can see that if we replace both this HS with deuterium, here we get, right, then we get an S enantiomer, right? And if we replace this HR with deuterium, we get the R isomer. Here you can see by replacement of the prochiral hydrogen, we are getting enantiomers. Then these hydrogens are called enantiotopic. And in case if replacing the 2 hydrogens by some other substituent, we get diastereomers, then these 2 hydrogens will be called as diastereotopic hydrogens, right? Just consider this example. So again, we have 2 prochiral hydrogens. This is not a chiral center because it has 2 groups that are different and 2 groups that are same. Again, we have designated them as pro-S and pro-R. But you can see that if we convert any of these substituent into another substituent, right, then we can get a chiral center. So if I replace HS with deuterium, then what I get is a diastereomer. Similarly, if I replace this HR with deuterium, I get another diastereomer, right? So if replacing any of the prochiral hydrogens with another substituent result in formation of a diastereomer, then these hydrogens are called diastereotopic hydrogens, right? So if you replace a prochiral hydrogen with some other group and you get an enantiomer, then those prochiral hydrogen will be called enantiotopic. And if you replace a prochiral hydrogen with other substituents and you get a diastereomer, then the hydrogen will be called as diastereotopic hydrogen. Right. So if the hydrogens that are completely identical, and if you replace those hydrogens with some other groups, then you cannot get a chiral center. Such hydrogens are called homotopic. Homo means same. So it doesn't matter if you replace these hydrogens with some other groups, so you can never get a chiral center. For example, again we have a ethanol molecule, you can see. So here you have a hydroxyl group, a prochiral center, HS and HR, we have already assigned, and we have a methyl group here. So if I replace any of the hydrogens with some other substituent, I'm not getting a chiral center, right? So these three hydrogens are identical, so you cannot get a chiral center by replacing any of these hydrogens with any other substituent, right? So therefore the methyl of this ethanol is called a homochiral center. It's a homotopic hydrogen, right? So this is homotopic and these are enantiotopic, and if we get a diastereomer by replacing these hydrogens, then this would have called a diastereotopic center, right? So groups other than hydrogen can be considered as prochiral as well. For example, so here you can see that we have a molecule here. So here we have hydroxyl and we have ethyl, and we have two methyl groups here. But if I replace any of these methyl with some other group, then the center will become chiral. So these methyls are called prochiral, right? It's not necessary that prochirality is only associated with hydrogen. So you can have any other group which can also be prochiral. So in this specific case, we have methyl, which is prochiral, right? So you can make the designation. So just replace this methyl with some other group, right, and see what configuration you get. So this is pro R and this is pro S, right? So in that case, if you are considering how to assign this configuration pro R and pro S, then just replace any of these groups with some other substituent and assign the configuration. So you have to assign higher configuration to that group. So 1, then you have the 2, and this is 3, right? So in that case you can get the configuration. Just assume that you have replaced this methyl group with some other group, right? One thing that's important for you to know, that the easy isomers, they are considered as diastereomers, although there is no chiral center in this system, right? It's an alkene, but although it's an alkene, but it is considered as a diastereomer. So if the alkene is differently substituted, then that will be considered as a diastereomer, right? So here you can see that this alkene is not a stereoisomer. Why? Because these two hydrogens on this carbon, they are the same, right? But if I replace any of these hydrogen with some other group, then that will become a diastereomer. You can see? So this is prochiral center. This carbon is called prochiral center. These hydrogens are called prochiral. And since replacement of any of these hydrogens with some other group will result in formation of a diastereomer, because easy isomer will be formed and easy isomers are diastereomers, therefore the replacement of any of these hydrogens with some other group like deuterium will result in formation of a diastereomer, right? So by replacement of this hydrogen by deuterium, we get V isomer and E isomer. So these are diastereomers, and these two hydrogens are considered as diastereotopic hydrogens, right? So just like we have alkenes, we have carbonyl compounds, so and imines. So these alkenes have double bond The carbonyl have double bond, the imines have double bond, but the difference is that alkenes have a double bond between carbon and carbon. Carbonyl has a double bond between carbon and oxygen, and imines have a double bond between carbon and nitrogens. Right? So the carbonyl group is not a prochiral, it's not a chiral center, right? It's sp2 hybridized carbon, it's not a chiral center. Similarly, the iminic carbon is not a chiral center at all, but they are considered prochiral. Right, so why we are considering them as prochiral? Because you can see if you have a carbonyl group here and we have two groups here, right? So provided that these two groups are different, suppose this is R1 and this is R2, right? So provided that if two groups are different, if I add something additionally on this double bond which is different, for example, if I bring another substituent like X on this chiral center, so all groups to this carbon will become different, right? So this will become a chiral center, you can see, right? So if the two groups attached to the carbonyl, if these two groups are different, then by bringing another group on this carbon, we'll convert that into a chiral center. So although it's not chiral center, but it can form a chiral center. Therefore, the carbonyl compounds are considered, the carbonyl carbon is considered as a prochiral center. Just like a carbonyl group, so we have an imine group here. So in imines, we have a carbon-nitrogen single bond. So you can have hydrogen here, any other group here, and we have two groups attached to the carbon. Again, these two groups should be different, right? Suppose R1 and R2. So although this is not a chiral center, but if I add something on this carbon which is different, then all the four groups attached to this carbon will become different, so it will become a chiral center, right? So for that reason, we are saying that carbonyl and iminic carbons are prochiral center, although they are not chiral, but they can form a chiral center when another substituent is attached to that. So the carbonyl groups have a planar geometry. You can say it's a flat molecule here. Similarly, the imine, it has a flat surface here. So you can see the carbonyl from above and the carbonyl from below, right? So these above and below surfaces of the carbonyl, they are considered as faces of the carbonyl. Similarly, you have faces of the imine. So if you see the imine from above or you see the imine from below, so these two surfaces of the imine, they are considered as the faces of imine, and the faces are designated as reface and psi-face. So in order to elaborate this concept, let's consider a carbonyl system, right? So here we have a oxygen or nitrogen here. So if you have oxygen, this is a carbonyl system, and if you have nitrogen here, then you will have an imine here. So you can see that these two groups are different. So if you are seeing this molecule from the front, as I am saying, so just say, imagine that I am looking at this molecule on the surface, right, on the front side. So this phase, if I designate them, so here we have one group, this is highest priority because it's oxygen or nitrogen, and suppose this group has second priority, so it has been designated as, so it has been designated as 2, while this group has been designated as 3 because it has the least preference. So going from highest to lowest preference, you can see I am going clockwise. So this phase, this surface of the imine or the carbonyl is known as re-surface. Re means clockwise, right? And if I see this molecule from behind, so if I just flip the molecule, so if I flip the molecule here, so this situation will be that. You can see that if I flip the molecule, right, or if I see the molecule from back side, so this molecule will appear like this one, right? So here you can see this is oxygen at the same place, but the position of 2 and 3 have been interchanged. This is when you are looking for the molecule from the behind surface. So if I go from 1, 2 and 3, so the direction is anticlockwise. So anticlockwise is known as psi. So this surface of the carbonyl or imine is known as psi surface, right? So if I see the molecule from the side, right, so 1, 2 and 3, right, this is called the re-surface, while in case if I see the molecule from the back side, then in that case this surface is known as psi. So if I see the molecule from this side, from the front surface, this is Re, while if I see the molecule from this angle, right, then the surface will be known as the psi surface. Okay, now we have enantioselective reaction. So in order to describe an enantioselective reaction, just remember that if in a reaction a prochiral center side, assume that you have the concept of prochiral center in your mind, that if you have a center which is not chiral but it can be converted into a chiral center by replacement of any of a hydrogen or any of the group with a substituent, right? So if a reaction prochiral center result in formation of an enantiomer in preference to the other enantiomer, right? So if a prochiral center can form two enantiomers and one of the enantiomer is formed in preference, whether you use a chiral catalyst or use enzyme or you use a chiral reagent, right, whatever the conditions, but if a prochiral center result in formation of two enantiomers of which one enantiomer is formed in preference, such a reaction is called enantioselectivity. So whenever you have an enantioselective reaction, then the selectivity is determined by enantiomeric excess, right? So enantiomeric excess tells you that which of the isomer is formed in preference, right? So whether it's the R isomer which is dominating or it's the S isomer which is dominating, right? Another concept is optical purity. So optical purity is a way to describe the composition of a mixture, right? So it means that whether the sample you have or the reaction mixture you have, it has a net optical rotation or not, right? So in order to calculate the percent optical purity, so we have this the optical rotation of the sample and we have optical rotation of the pure isomer, right? For example, if you want to convert if you are considering optical purity of reaction mixture that has camphor, so camphor has if in pure form it has an optical rotation value. So you take the optical rotation value for the pure camphor, for the pure enantiomer, right? And you take the optical rotation value for the reaction mixture, right? So in order to calculate the percentage optical purity, we divide the optical rotation of the sample by optical rotation of the pure enantiomer and multiply it by 100. So in that case, we can get how much pure isomer is present in our sample, right? So how much pure enantiomer is present in the sample, this is known as the optical purity of the sample, right? And when you are considering that which of the enantiomer is dominating, so what percentage of S is forming or what percentage of R is forming, then we can get it from the enantiomeric excess. The formula of enantiomeric excess is the concentration of the R isomer minus concentration of the S isomer that's formed, divided by the sum of concentration of R and S multiplied by 100. So in that case, we can get the percentage of R minus percentage of S, right? So we'll see that which of the isomer is dominating, right? So enantiomeric purity is determined numerically, right? But it has to be experimentally determined, right? So here we have example of enantioselective reactions. So enantioselective reactions are also known as the asymmetric synthesis. So whenever you see this term of asymmetric synthesis, just remember that this is the enantioselective reaction. For example, we have this acetone and we are reacting with paranitrobenzaldehyde, right? This is the aldol reaction. So we are getting an aldol. So you can see that here we have a chiral center because this carbon has four groups, different groups attached to it. So we have a hydroxyl group, here we have a phenyl group, and here we have a CH group, and the fourth group is the hydrogen, which is below the plane. So this reaction is resulting in formation of the product in 68% yield. However, this isomer is forming in 76% excess, right? You can see this isomer is forming 76% in excess than the other isomer. So the percentage of the other isomer will be 24%, right? So you can see that this reaction, it can form two isomers, but this isomer is forming in excess. So this reaction is preferring the formation of this product, right? So this is known as an enantioselective reaction. because this reaction is preferring the formation of one of the two enantiomers in excess. Now we have an example of diastereoselective reaction. So if in a reaction the reactant is an enantiomer, right? So diastereoselective reactions normally have a starting material which is an enantiomer, right? So you can see here that this molecule has one chiral center, right? So this is an enantiomer. So when we carry out the reaction of this enantiomer and we convert a prochiral center, so you can see here is a carbonyl system, so carbonyl is a prochiral center, right? And we are adding this hydride on this carbonyl system, right? So we are converting this prochiral center into a chiral center. So you can just imagine that the product will have two chiral centers, one that is existing and the other that will be newly formed. So if your product has two chiral center, then such a product is called a diastereomer. It will be a diastereomer, right? So here the reactant is an enantiomer, and the enantiomer is being converted into diastereomer, so you can form two isomers, two diastereomers, depending on the hydride, whether it's coming from the back side or it's coming from the front side, right? So if the hydride is coming from the back side, product will be this one, but if the hydride is coming from the front side, then the product will be this one. So you can see here that we are getting two diastereomers, but the yields of the diastereomers are different, you can see. So in case if you're using lithium aluminium hydride, then this isomer is formed in 76% excess, while this isomer is formed in 24% excess. So this reaction is diastereoselective. While when you use the diol, then in that case you get this isomer in 100% yield, while this percent reaction is not, this product is not forming at all, right? So this reagent is resulting in 100% selectivity. So this reaction is 100% diastereoselective, right? So if a reaction is 100% stereoselective, we say that this reaction is stereospecific, right? So whenever you have 100% selectivity, then 100% selectivity is mostly called specificity, right? So specific reaction, stereospecific reaction is a reaction in which the stereochemistry of the reactant completely determines the stereochemistry of the product without any option. For example, if the product is R and we say that if the reactant has R configuration, and we say that product will definitely have R configuration, so here you can see that the reactant is determining the stereochemistry of the product. So if there is no other option and the reactant is completely determining the stereochemistry of the product, then we say that the stereospecific reaction will be occurring, right? And the stereospecific sometimes used to mean 100% stereoselective reaction, right? So whenever there is no other option, so normally you see that whenever we are considering a mechanism, so the reaction mechanism may involve formation of two products by different route, but if there is only one route possible, then such reaction will be considered as stereospecific, right? And 100% stereoselectivity is also considered as stereospecificity. So this is the end of lecture. I suppose that you have understood about the basics of stereoselectivity. So what we mean by stereoselectivity. Also, we have studied terms like the prochiral, homochiral, enantiotopic, diastereotopic, and we have also seen the terms of enantiomeric excess, optical purity. I hope you have understood it well. Thank you for your attention.